Hello, today I'm going to work through a set of questions that you might typically get in an A2 level physics exam on classical mechanics. First, let's review all the formulae that you may need. Depending on your exam board, sometimes you'll be given these formulae, but sometimes you'll be expected to remember them. These are key formulae in classical mechanics, so it's worth trying to get them into your head. So let's go through them. For Newton's laws of motion, we will need V equals u plus at, where v is final velocity, u initial velocity, a acceleration and t time. S equals ut plus half at squared, where s is the distance covered. V squared equals u squared plus 2as. V bar equals v plus u over 2. That's the average speed, if you have constant acceleration, is the final speed plus the initial speed divided by 2. F equals ma, force is mass times acceleration. Kinetic energy is a half mv squared, and potential energy near the Earth is mgh. Then we need the formulae for power, work and momentum. Work done is force times distance, or if the force is not applied if the force is not applied in the line of the distance that you're going to push the body, then it's F cos theta, the angle between the force and the direction of movement. Power is work over time, measured in watts. Power is also force times velocity, because work is force times distance, and so force times distance over time is force times distance over time, which is velocity. Momentum is mass times velocity. Now we come to springs and stretching. Force is the spring constant, or the stiffness constant, times the displacement. Stress is force over area. Strain is extension over original length. Young's modulus is stress over strain, so that's going to be force over area divided by extension over length, which is force times length over extension times area, and that's measured in newtons per metre squared. Then we come to circular motion. The velocity is equal to the radius times the angular velocity. Angular velocity is 2 pi times the frequency of rotation. Frequency is 1 over the period. Centripetal acceleration, which is directed towards the centre of the circle, is v squared over r, or omega squared r. Centripetal force is mv squared over r, which equals m omega squared r. In other words, it's just the mass times the centripetal acceleration. Then for simple harmonic motion, we have that acceleration equals minus omega squared times the displacement x. Omega squared for a spring is k, the spring constant, divided by m, the mass at the end of the spring. Omega squared for a pendulum is g, gravity, divided by l, the length of the pendulum. The maximum acceleration, which of course takes place when the either the spring or the pendulum is at its maximum displacement, is minus omega squared times a, where a is the maximum amplitude. The velocity at any point is equal to plus or minus omega times the square root of a squared, the amplitude, minus x squared, the displacement, squared. The maximum velocity, which of course will be as the mass on the spring, or as the bob of the pendulum passes the midpoint, is omega a. You can measure the displacement x, it's a cosine omega t, if you are measuring time from the maximum displacement. In other words, if you start the clock when the bob or the spring is at its maximum displacement, or x equals a times the sine of omega t if you start the clock when the mass on the spring or when the bob on the pendulum are passing their midpoint. And then the t, the period of the oscillation, is 2 pi over omega, which for a spring means it's 2 pi times the square root of m over k, or for a pendulum it's 2 pi times the square root of L over G. Question 1. A small ball weighing or having a mass of 0.4 kilograms is travelling at 5 meters per second. It hits a stationary ball which has a mass of 2.5 kilograms, and after that collision we end up with the small ball travelling back in the opposite direction at 2 meters per second, and we're asked to find the velocity of the larger ball. Well, we're going to use the conservation of momentum, which says that the momentum before, which is mass 1 times velocity 1, mass of the small ball times its velocity, plus the mass of the large ball times its velocity, is equal to the mass of the small ball times its new velocity after the collision, plus the mass of the large ball times its velocity after the collision. This is conservation of momentum. So the mass of the small ball is 0.4. Its velocity before the collision was 5 meters per second, plus the mass of the large ball was 2.5 kilograms, but its velocity was 0. So effectively that term goes, is equal to the mass of the small ball, which is 0.4, times its velocity after the collision. Well, we're going to use going from left to right as being the positive direction. So if you're moving from right to left, that's the negative direction. So this is times minus 0.2. Times 2, because it's travelling at 2 meters per second in the other direction. Plus the mass of the large ball, 2.5 kilograms, times its velocity after the collision, which we're going to call v4, and that's what we don't know. So now we've got 0.4 times 5, which is 2, plus nothing, is equal to minus 0.8 plus 2.5 times v4. And I think I can leave it to you to do the calculation from that, but that will give you that v4 is equal to essentially 2.8 divided by 2.5, and that equals 1.12 meters per second. So the velocity of the large ball after the collision will be 1.12 meters per second because momentum is conserved. Question 2. We have a 1 kilogram block travelling at 3 meters per second, hitting a stationary block which has a mass of 1.5 kilograms. The two join together and continue to travel at velocity v. What is velocity v? Well, once again, we're going to say that momentum before the collision is equal to momentum after the collision. What is the momentum before the collision? Well, the momentum of this is mass times velocity, so that's 1 times 3. What is the momentum of this? Well, we don't need to bother. It was stationary, so mass times velocity is going to be 0. So momentum before is this. What is the momentum afterwards? Well, now we've got a combined mass of 1 plus 1.5, which is 2.5, times the velocity v, which is the velocity of the coupled arrangement. And so now you've simply got that v is equal to 3 divided by 2.5, and that equals 1.2 meters per second. So the velocity with which this coupled unit will move to the right will be 1.2 meters per second. Question 4. What is the angular velocity with which the Earth rotates around the Sun? And we are encouraged to consider that this is a circular orbit. In fact, it is of course elliptical, but we're going to assume that it's circular for these purposes. And we want the angular velocity, which means we're looking at the number of radians per second that the Earth sweeps out as it goes round the Sun. Well, we know that it does 1 complete revolution in a year, and 1 complete cycle or revolution is 2 pi radians, so the Earth must do 2 pi radians in 1 year. So that is, in a sense, its angular velocity, 2 pi radians per year. But actually this should be expressed in seconds, and 1 year is 365 days times 24 hours in each day times 3,600 seconds in every hour. And so now you get that the Earth does 2 pi radians in every 3.2 times 10 to the 7 seconds. So if you want to know what the angular velocity is in radians per second, that is going to be 2 pi divided by 3.2 times 10 to the 7, and that works out at, so this is the, as it were, the angular velocity, which is omega, and that is going to be 1.96 times 10 to the minus 7 radians per second. Question 5. What then is the linear speed of the Earth? In other words, what is the speed that it goes round the circumference of the circle? And we are told that the radius of the Earth's orbit is equal to 1.5 times 10 to the 11 meters. Well, here we can simply use the formula which we had at the beginning, that the, as it were, the tangential velocity, the orbital velocity, is equal to the angular velocity times the radius. So v is going to be the angular velocity that we just calculated, 1.96 times 10 to the minus 7, times the radius, which we've been given, is 1.5 times 10 to the 11. And if you simply multiply that out, you will get that that is equal to that v, the tangential velocity, is 2.94 times 10 to the 4 meters per second. So the Earth is hurtling around the Sun at a linear velocity of nearly 30,000 meters per second. Question 6. What then is the centripetal force associated with the Earth's orbit around the Sun? In other words, what is the force between the Earth and the Sun that is essentially keeping the Earth in circular orbit? Well, here we're going to use the formula for centripetal force. F equals mv squared over r, or we could say it is equal to m omega squared over r, where m is the mass of the Earth, and we are given the mass of the Earth as equal to 6 times 10 to the 24 kilograms. So now we can use either of these formulae. I might as well use this one, m omega squared. Sorry, this is m omega squared r. What am I talking about? M omega squared r, so it's mv squared over r, or m omega squared r. Should have spotted that. So now we just substitute in here. We've got the force is equal to m, which is 6 times 10 to the 24, times omega, which we calculated back up here, 1.96 times 10 to the minus 7. So this is now times 1.96 times 10 to the minus 7 squared, because it's m omega squared, times r, the radius, which we were given as 1.5 times 10 to the 11th meters. So now we multiply that by 1.5 times 10 to the 11. And that all comes out at 34.57 times 10 to the 21 newtons. And that's a large centripetal force, but then it would have to be, because it's got to keep the whole Earth in circular orbit. Question 7. I want to swing a bucket of water around and over my head. So here I am holding a bucket of water. This is my arm here. This is the bucket, and I'm going to swing the bucket so that it goes over my head and back down onto the ground again. Indeed, I'm going to keep swinging it round. Now the question is, how fast do I have to swing it in order for the water not to fall on my head? In other words, what is the frequency of rotation that I need to achieve, the minimum frequency to stop the water from falling out? And we're going to assume that the radius of this circle is r. R is 1 meter. That's about the length of my arm plus the bucket. So let's assume that the mass of the bucket is mb, and then we've got this condition, that in order for the water not to come out, the force due to the bucket and the water, the mb is the mass of the bucket and the water, the force due to the bucket plus the water, which is mg, is going to have to equal the centripetal force, m omega squared r. Now the masses, of course, cancel, so that was the mass of the bucket, so we don't need to worry what the mass is. It doesn't matter how much the bucket may have as a mass, because it will always get the same answer, and that gets you that omega squared is equal to g divided by r, which is 9.81, divided by the radius, which we've told was 1 meter, so that's easy. That gives you that omega squared is 9.81, which means that omega, the angular velocity, is the square root of 9.81, which is 3.13. but we actually want the frequency, and omega of course is 2 pi f. So the actual frequency of rotation is 3.13 divided by 2 pi, which comes to 0.498 revolutions per second, or if you like, 1 cycle every 2 seconds. So as long as I swing the bucket over my head, it matters not what the mass of the bucket is or how much water you've got in it, as long as you swing it over your head at least once every 2 seconds, you won't get wet. You may like to try it, but I suggest you do so outside and wearing clothes that you don't mind getting wet, just in case you don't manage it first time. Question 8. Here we have a man who is shooting some kind of missile at a target, and the target is on a wall which is 500 meters away from where he's standing. He lines up the missile firing device onto the target so that he's looking at it directly, so that this is a straight line, and it happens to be at 30 degrees to the horizontal. And then he, having lined it up in this way, he fires the missile. And the question is, by how far will it miss the target? Now, the reason it will miss the target, of course, is because this man has not done A2 level physics. He doesn't realise that that missile is not going to go in a straight line because gravity is going to act on it, and it is instead going to curve like that, and it's going to miss the target by that amount. And we've got to find out what it is. The missile is travelling at 200 meters per second. Well, remember that we can always resolve the velocity of the missile into its component parts. So what we've essentially got is, if we draw the XY framework, the actual velocity is 200 meters per second at an angle of 30 degrees. So the horizontal component is going to be 200 times the cosine of 30. And the vertical component is going to be 200 times the sine of 30. And each of those can be regarded as independent. 200 times the sine of 30, well, sine of 30 is a half, so that will equal 100 meters per second is the vertical component of the velocity, and 200 times the cosine of 30, well, cosine of 30 is 0.866, so that comes out at 173.2 meters per second in the horizontal direction. And the point is that gravity will act on the vertical direction velocity, but it will have no effect on the horizontal direction velocity. So the next thing we can do is to calculate the time it takes for this missile to travel the horizontal distance of 500 meters. Time is simply distance divided by speed, or velocity, and that is going to be 500 meters divided by the horizontal velocity, which we just calculated, 173.2, and that is going to be 2.88 seconds. So it takes 2.88 seconds for this missile to arrive at the wall. So now the question is, what is the vertical height of that wall? Or sorry, what is the vertical height that it will reach when it gets to the wall? For that we need the equation S equals ut plus a half at squared, and that's going to equal ut, well, the vertical velocity, remember we calculated, was 100, so that's u is 100, times t, well, we just calculated that, that's 2.88, plus a half times a, which is acceleration, which is acting downwards, so that will be minus 9.81, times t squared, which is 2.88 all squared. And that is going to be, well, this here is going to be 288 plus a half, or sorry, it's minus a half times 9.81 times 2.88 squared. And that's going to give you that S, which is the distance it moves up the the height above the firing position, in other words, the total distance will be 247 0.32 metres. So that's the height that it reaches above the firing position up the wall. But the question we want to know is, where was the target? Because then we can work out how far short we've got. Well, this is just a straightforward problem. We've got that the height of the target above the firing position divided by 500 metres is the tangent of the angle 30. So what you've now got is that the height of the target divided by 500 is equal to the tangent of 30. And the tangent of 30 is 0.577. And so that will give you that h is equal to 288.67 metres. So what have we got? We've got that the height of the target above the firing position was 288.67 metres, but the actual missile will reach 247.32 metres. So the extent by which the missile will miss the target is that height minus that height, which is 41.36 metres. So he's going to miss by quite a lot. Just to remind you, let's look at the diagram again. The height of the target above the firing position, which is essentially that distance, is going to be what we measured by saying that the height over 500 is equal to the tangent of 30. But the height, which is actually not x but s, above the firing position, which is where the missile will reach, was the other value we calculated, and the one minus the other gives you the difference, and that's the extent to which the target is missed by 41.36 metres. Question 9. A pendulum has a length, which is swinging backwards and forwards this way, has a length of 20 metres. And what I want to know is, how long does it take to do one complete cycle, which means it swings one way and then back again. How long did that one cycle take? For this, we're going to use the formula that the acceleration equals minus omega squared times x, the displacement, and for a pendulum, omega squared is L, the length of the pendulum, divided by g. Well, you're told that the length of the pendulum is 20. You know that g is 9.81, so that gets you 2.038. And so omega is going to be the square root of 2.038, which is 1.42. But omega, of course, equals 2 pi f times the frequency. And that means, and that's also equal to 2 pi divided by t, because the frequency is 1 over t. So now you've got that t, this produces t is equal to 2 pi over omega, which is 2 pi divided by 1.42. And that will give you that t is equal to 4.4 seconds. So it takes 4.4 seconds for the pendulum to do one complete swing back and forth, one complete cycle. Question 10. Here we have a pendulum. Its frequency is 1.5 hertz, so it swings 1.5 oscillations per second. It has a maximum displacement of 0.05 meters, and we're asked for three things. Firstly, what is its maximum velocity? What is its displacement after 0.1 seconds? And what is its time to fall to 0.01 meters from the midpoint? And the assumption is that the pendulum starts, and the time starts, when it is at its maximum displacement, and then it falls through one complete cycle. Well, its maximum velocity, of course, is when it's going through the midpoint, and that we saw in the formulae that we devised earlier. The maximum velocity is omega times the amplitude, and omega is 2 pi f, so it's 2 pi fa, which is 2 pi times the frequency, which is 1.5, times 1.5, times the maximum amplitude, which you were told was 0.05, and that gets you 0.47 meters per second. So the maximum velocity as it goes through the midpoint, 0.47 meters per second. We now need to know the displacement, that is the displacement from the midpoint after 0.1 seconds. So when you let go, after 0.1 seconds, how far away from the midpoint will it be? And again, we had a formula for that. It was that the displacement is equal to the amplitude times the cosine of omega t, which of course is the same as the cosine of 2 pi f times t. That is the case if you start the clock from the maximum displacement. If we had started the clock here, then you would use a sine term rather than a cosine term. So once again, we've got the displacement will be x, that's what we're trying to find, times the maximum displacement, which we were told was 0.05, times the cosine of 2 pi times the frequency, which was 1.5, times the time, which we were given or were asked was 0.1. And if you work that out, I think you'll find that the displacement comes to 0.029 meters. So after 0.1 of a second, the maximum displacement, which was 0.05, the bob has now moved to a position where from the midpoint it is now only 0.029 meters. And the third question we had to answer was how long does it take for the bob to fall to a position where it is only 0.01 meters from the midpoint? Well, once again, we can use this formula here. So let's rewrite it. X is equal to the maximum amplitude times the cosine of omega t, which is 2 pi f times t. This time it's the time that we're trying to find. We know that x, what x is, it was given to us as 0.01. So 0.01 is equal to the maximum amplitude, which you may remember was 0.05, times the cosine of 2 pi times the frequency, which is 1.5, times the time that we don't know. And that will give you that if you bring 0.05 on this side, that's 0.2 is equal to the cosine of 2 pi times 1.5 is approximately 9.4 times t. And now you have to do the anti-cosine, as it were. That gets you that 9.4 t is equal to 1.37. And so t is equal to 1.37 divided by 9.4, which equals 0.15 seconds. So it takes 0.15 seconds from the maximum displacement before it is a displacement of 0.01 meters from the midpoint. Question 11. We're given a spring and we're told that when there is no mass on the spring, its natural length is 0.2 meters. When you put a 0.2 kilogram mass on the spring, then it will extend to 0.4 meters. And we're asked to find several things. Firstly, what is the spring constant or the stiffness constant K? And secondly, if we pull this mass down a small amount and let go so that it now oscillates, what will the period of the oscillation be? Well, to find the stiffness constant or spring constant, we use the formula that the force is equal to the stiffness constant K times the extension, which means that K is equal to F divided by X. And that gives us that K is equal to the force, which is 0.2 kilograms multiplied by gravity, so it's mg is the force, divided by the extension. Well, the extension, when the spring was had no load, it was 0.2 meters. When it had the load, it was 0.4 meters. So the extension is the one minus the other, which is 0.2 meters. Actually, the 0.2's cancel, and so you get that the spring constant is 9.81, and that will be in units of newtons per meter, since it's force divided by length. If we set that spring oscillating, what will be the time period of oscillations? Well, we'll recall that the time period for an oscillation of a spring is 2 pi times the square root of m over k, and that equals 2 pi times the square root of the mass, which was 0.2, divided by k, which we just calculated, was 9.81. And if you do all that, you should get that that comes to approximately 0.9 seconds. So it takes 0.9 seconds for the spring to do one complete oscillation. Question 12. We have two pendulums. One is 0.2 meters long, the other is longer. And we swing them, and what we find is that when this pendulum has swung 6 cycles, this pendulum has only swung 4 cycles. And the question is, what is the length of this pendulum? So what we know is that the time for this to do 6 cycles is equal to the time for this to do 4 cycles. So let's say that the time period for this is t1, then 6 lots of 1 cycle for this is equal to 4 lots of the cycling for this. We'll call that t2. And we know that for a pendulum, the period of oscillation is 2 pi times the square root of L over G. And so now we've got that on this side we've got 6 times 2 pi times the square root of L, which we were given, it's 0.2 meters. So 0.2 divided by G, which is 9.81, is equal to, on this side, 4 times 2 pi times the square root of L, which we don't know, divided by G, which is 9.81. You'll notice that you've got the square root of 9.81 on either side, so that can cancel. And if you then simply take that to its basis, you'll find that L is equal to 0.45 meters. That's just a straight calculation. And finally, question 13, we've got a roller coaster. The car on the roller coaster comes down the slope, round the loop, and off. And the question you're being asked is that you have to show that the height h, which is the height above the ground that the car starts, must be at least 2.5 times the radius of the loop. Well, what we can say is that the car will have potential energy at this point. When it gets to the ground, all that potential energy will have been converted to kinetic energy. And then when it gets back up here, it will have some potential energy because it's gone back upwards again, and it will have a reduced kinetic energy. But that the energy at all stages will be constant. So let's first of all think about the car coming down here and reaching this position here. At this position it will be travelling at a velocity v, and we can say that the potential energy that it had when it was at the top of the roller coaster, which is mgh, where m is the mass of the little car, and h of course is the height above the ground, will be converted into, and therefore will be equal to, a half mv squared, and that's the kinetic energy it will have at this position here. Let's suppose that when the car is coming round the loop, it is travelling at a velocity u. Obviously that will be less than v because some of the energy has been converted into potential energy. What is the condition for going round in that circle such that you don't fall off? Basically, the gravitational force must equal the centripetal force, which means that mg, the mass of the car, times g, must equal the centripetal force, which is mu squared divided by r. The m's cancel, and that gets you the formula that g is u squared over r. So now we can write that the potential energy that the car had when it was at the top of the roller coaster, which is mgh, must equal the sum of the potential energy and kinetic energy that the car has when it's at the top of the loop. Its potential energy will be mg times 2r, because the height above the ground is twice the radius, plus its kinetic energy, which will be a half mu squared. But u squared, you will see, is equal to g times r. U squared is g times r. So I can cross this out and put instead a half of m times u squared is g times r. And now you'll notice that mg cancels throughout. mg, mg, mg. And we get that h is equal to 2r plus 0.5r, which is 2.5r. And so we've shown that h must be at least 2.5r if you want the little car to go round the loop without falling off.